All right, Gen Chem, we are going to talk a little bit more about solubility today and also start learning how to do calculations of concentrations. So when we left off last time, we talked about how solubility of solids in liquids tend to increase when the temperature of that solvent increases. And we determined that by looking at this graph that we have right here. You notice as the temperature increases, the solubility lines of almost all of these compounds also increase. So warmer water or warmer solvent, whatever we're using as a solvent, tend to be able to dissolve more things. And that's why we like to wash things in hotter water, because it actually gets things cleaner because things are more soluble. Now this time we are also going to start looking at the solubility of dissolved gases in solvents. So we use dissolved gases a lot, actually. So when we think of dissolved gases, probably the best thing that you understand dissolved gases is when you open up a can of soda pop. So we're going to think of this as we think of soda pop, okay? So if we look at the solubility of different gases, notice as the temperature increases of that solvent or that liquid, the solubility or the ability to have these gases in solution actually decreases. And we understand that just by nature of if we keep a can of soda pop outside the fridge and let it get cool, or not cool, but let it warm up to room temperature, doesn't all that fizzy gas leave that soda pop? It will leave that soda pop because that water is getting warmer, and so that carbon dioxide, the fizzy stuff, is actually becoming less soluble. So it escapes out of the water. So that's when warm soda pop, that's why it tastes flat when we let it get warm. Okay? So if we look at this, what happens to the solubility of gases when temperature is increased? The solubility of gases decreases. Gases decrease when temperature is increased. So the warmer we make that solvent or that liquid, the less gas that we're going to be able to dissolve in it. Okay? So the profundity is that as temperatures increase, solubility of gases decrease. Okay? So here we go. So solids are pretty much the opposite of gases when we're trying to dissolve them. So the solubility of solids generally increases with an increase of temperature, but the solubility of gases always decreases with the increase in temperature. So you're going to want to know both of those things very well. So how many of you guys actually go out and go fishing? Okay? If you've ever gone fishing, when you get a fish up out of that lake or that river or that stream, how do those fish actually get their oxygen? They have gills on the side of their head, don't they? And those gills allow them to transfer oxygen from the water into their lungs. Now, are they breaking the water apart like the H2O? Are they breaking that oxygen off of the water? No. They're using dissolved oxygen that is dissolved in the water. So they get their oxygen from dissolved oxygen in the water. Okay? So think about this. Have you ever had a goldfish? Did you ever not change their water regularly? what happened to your goldfish? If you didn't change that water regularly enough, that goldfish died. And the reason that goldfish died is that oxygen wasn't recirculated enough unless you had a pump or a valve in there somewhere. So, because that goldfish used up the oxygen that was dissolved in the water. So the goldfish used up the dissolved oxygen and needed more. So essentially, if you don't change that water in your fish tank regularly, or you don't have an air pump filtering air in there all the time, you're suffocating your fish. Okay, how many of you guys actually go trout fishing? If you've ever gone trout fishing, you know that the trout actually hide out in the really deep pools in the summertime, especially in the summertime. Now, what's the difference between the water in the deep pools versus the water in the shallow pools? Do you think about that for a second? If you think about it, the deep pools are really cold, right? So the deep water or the deep pools in the stream are the cold places. And what did we say about the solubility of gas with temperature? We said it decreased as the temperature went up. So if temperature goes up, the solubility of the gas goes down. So if the temperature is cold, if the temperature goes down, the solubility is going to go up. So in those cold places, that actually has more oxygen than the rest of the stream. The cold places, or those deep pools, have more dissolved oxygen. And because they have more dissolved oxygen in them, that makes it easier for the trout to breathe. If you've ever put trout into warm water, they die pretty quickly because they suffocate. They don't get enough oxygen. Trout actually need a lot of oxygen because they're a very fast fish, and because of that, their muscles burn up a lot of oxygen. So they need a lot of oxygen. So let's think about this. Why do we keep our open soda pop bottles in the fridge? The colder we can keep it, the more that carbon dioxide is going to stay dissolved in that solution. So it's not going to go flat. So the colder we can keep the soda pop, of course, without freezing, because we don't want to freeze it, the more carbon dioxide, those are the bubbles that gives it the carbonation, the more carbon dioxide can stay in solution. That's a really fancy, long way of saying that soda pop won't go flat. The soda pop won't go flat. Okay, so the colder we can keep that soda pop, the longer it will stay bubbly and not flat. All right, now we're going to start talking about molarity. Molarity is a unit of concentration. So molarity is designated with a big capital M. Wow. Wonder why that just jumped. And it's probably going to jump on me again, because that's what it likes to do. Okay, so let's see about this. Wow, and it totally took the stuff that I wrote and put it not where I want it. So, molarity. Let's put this in a different color so it doesn't get confusing. Molarity is given to us by a big capital M. Yep, and it just jumped again, just like I thought. Okay, molarity. Let's get this down. Molarity, big capital M. So, molarity is a measurement of the number of moles of solute divided by liters of solution. Okay? Sometimes it's also shorthanded. We have shorthand the capital M. Sometimes we also shorthand with square brackets as well. So the capital M, square brackets, both mean moles of solute divided by liters of solution. Okay, molarity is a unit of solution concentration. It's one of the mathematical ways that we can represent how strong a concentration of a solution is. Okay, so once again, molarity is equal to number of moles of solute divided by liters of solution. Okay, so yes, we are going to use moles again, and eventually we will actually go from grams to moles and liters and do all those conversions. Today we're just going to keep it easy and just do moles per liter. Okay, so let's do some practice. You're going to want a calculator for this, so make sure you've got a calculator and make sure you've got some notes so that you can take some notes. Okay, so what is the molarity of the following solutions? So remember, we always want to have moles on top for molarity and liters on the bottom. So I have moles of copper 2 sulfate. So I have 1 mole of copper 2 sulfate, and my volume is 1 liter. 1 liter of solutions. 1 divided by 1 is 1, right? For the math. So I can write this as 1 capital M, and that was a horrible capital M. Let's try that again. One molar copper 2 sulfate. That is an easy way to do that. Or if I wanted to write it out, I could just say 1 mole of copper 2 sulfate per 1 liter of solution as well. Either way they're both different ways of looking at that concentration and how to write it. Okay, now if I have 2 moles of copper 2 sulfate, in 2 liters of solution, 2 divided by 2 is 1. So this is still the same concentration. So I would have 1 molar copper sulfate solution. All right? So let's look at C. What if I have 1 mole of copper 2 sulfate in 0.5 liters of solution? So 1 divided by 0.5. What do we have? It would give us 2. So that would be 2 molar copper 2 sulfate solution. Right? See if you can do the next 2 and check in just a little bit. Okay, D, I have 0.5 moles of copper 2 sulfate in 0.5 liters of solution. 0.5 divided by 0.5 is 1. So I will have 1 mole copper 2 sulfate. How'd you do on that one? Okay, E is a little bit trickier because I don't have this in liters now. I have this in milliliters. So you're going to have to convert this from milliliters to liters. Do you guys remember how many milliliters there are in a liter? I have 1,000 milliliters in 1 liter. So we're going to use that conversion. Okay, so I've got 0.25 moles of copper 2 sulfate, and it's in 250 milliliters of solution. I've got to get milliliters into liters. So I'm going to use this conversion that we did over here. I want my milliliters to cancel, so it needs to be on the opposite side. It's already on the bottom, so the opposite side is the top. So I'm going to put my 1,000 milliliters up top equal 1 liter. My unit of milliliters cancel. So let's see, 0.25 times 1,000 gives me 250 divided by 250 gives me 1. So that will give me 1 molar solution of copper 2 sulfate. Okay? All right. Next, we're going to learn a little bit about molality. Now, molality is also a different way that we do concentration. It's a little bit different. It's moles of solute divided by kilogram of solvent. We aren't doing a moles per volume here. We are doing a moles per mass of solvent. Not the whole solution, just the solvent. Okay? So, we also signify molality with a lowercase m. Not a big M, but a lowercase m. Okay? So it's a little bit different. So we're going to be doing moles per kilogram now. All right, so once again, we're going to need a calculator. Example 11, calculate the molality. So molality of a solution containing 1.5 moles. There's my mole, so I'm going to put that on top, right? So 1.5 moles of ethanol and I have 350 grams. Ooh, this needs to be in kilograms. So I have 350 grams of water, but I want my grams of water to be in kilograms. So how many grams are there in a kilogram? We're going to use this conversion. I have 1,000 grams equal 1 kilogram. So my grams are on the bottom, and I need my grams to cancel out. So on the next step, I'm going to put grams on the top so the grams cancel out. So I have 1,000 grams in 1 kilogram. So my grams cancel out, my grams of water. So now I have moles per kilogram. So I'm going to take 1.5 times 1,000. Everything on the top is a multiplier, and then everything on the bottom is a divider. So I'm going to divide by 350. Okay? So 1.5 divided by 350 times 1,000. My calculator gives me this, 0.42857 and stuff. So I've got 2 digits here, and I've got 4 digits here. So we probably should just do 2 digits. So 1, 2, that 8 tells me to round up. So I'm going to count this as 4.3 molal ethanol in water. So this tells me my solute, and this tells me my solvent. Okay, that is how you would write that. All right, let's do one more example. How many moles of acetic acid are needed to make a 0.5 molar solution, molal solution, not molar, molal, little m, molality, in 750 grams of water. So we're going to start with our grams of water, and we're going to convert that into kilograms first, okay? So I'm going to start, and it looks like my computer is freezing. So let's see if it will let me write. It's not. So let's give it a minute. So I'm going to start with my 750 grams of water. I need to get my grams of water into kilograms because this is my solvent. Okay? So this is my solvent, and this is my solute. So we're going to use this conversion up here that we used. So I have 1,000 grams of water in 1 kilogram of water. Okay, so my grams of water cancel out, and I'm left with kilograms, which is what I want. Now this molality actually gives me a ratio. It gives me a 0.50 moles per kilogram. And the moles are of acetic acid, HC2H3O2, and kilogram of water. Can I use this ratio to cancel out my kilograms of water? I sure can. If I put this kilogram of water on the bottom over here, it will cancel out the kilograms of water that I have on top. So I'm going to use my ratio, 0.50 moles of acetic acid are in 1 kilogram of water. Notice my kilograms of water cancel, and I just have moles of acetic acid left, which is what I'm asking about. So mathematically, everything on the top, remember, is a multiplier, and everything on the bottom is a divider. Okay, so I'm going to take 750, divide by 1,000. Then the next step, I'm going to multiply by 0.5. This gives me 0.375 moles of acetic acid. Okay, I've got 3 digits here, so I'm going to have 3 digits here. Okay, so your homework is going to be doing some of these molality, some of these molarity, and also some solubility of gases and solids. So good luck. If you have any questions, please come see me during flex time or email me. Thanks. See you later. Bye.